So yeah, here's planes explained for your point, for your brain. That's about 5 seconds. That's good. So first of all, anyone know how planes work? Okay.
Well, like how planes work, like the pressure difference between
Like basic theory on what makes a plane fly and not dive at the ground.
Well, you could have a pressure difference between the top side of the wing and the bottom side of the wing.
So more basic than
lift?
Lift, yes.
You mean like the forward lift?
Basically,
drag
yeah. So,
yeah.
So,
Lift pushes up more than weight pushes down.
yeah. And
When things with wings move very fast, they generate lift under their wings.
you. So the basic idea is lift has to be greater than the weight, and if you don't want to slow down eventually, your thrust has to be greater than your drag.
Lift has to be greater than weight while it's going up, right?
In level flight. At any time you don't want to start falling towards the ground, your lift has to be greater than your weight.
Oh,
So, how do, I noticed some people mention pressures on the wings, so how do wings work? Anyone?
This might be wrong, but you have the top side of the wing is longer than the bottom side of the wing.
Yeah.
So when air moves through it, you have low pressure on the top and high pressure on the bottom because of which law is that? A law. So
there's there's the Bernoulli equation. There's multiple other ways of doing it.
Pretty much the air on the bottom, let's go to the air on top.
The way that a lot of wings are taught, the way that wings are taught to most people before college is wrong, and that's the path length. So some people say that because the distance that the top wing that the top of the wing has to travel through the air is longer, that's why there's lower pressure, and that's completely incorrect. You can make a wing fly even if the bottom's long. So yeah, the major thing is you have the Bernoulli effect, and so that creates a difference in pressure on the wing. So you have low pressure on the top of the wing and high pressure on the bottom of the wing, and essentially the plane gets sucked up into the sky like there was a vacuum above it, because there is. You can also view it from a different perspective, which I prefer because it makes more sense to me, is wings turn airflow. That's all they do. And the magnitude of the lift on the wing is equal to the amount of air that it's turned, the amount of air that has been turned and is now being pushed downwards. So you can sort of see the airflow turning on this, and I don't know, that's a weird airfoil, but it's an airfoil. Yeah. So all that matters is the pressure differential of flow turning. So here are some different airfoils. So obviously there's a difference between the subsonic and the supersonic airfoils. Do people want to learn more about the subsonic ones or the supersonic ones?
Supersonic.
Okay, supersonic. They look different. They look pointy. So I don't actually have slides for the supersonic ones, but I'll go over the supersonic ones. So essentially, at every, so at the front tip, let's assume that the plane's going that way. So at the front tip, and essentially every corner, there's going to be a shock wave. And the reason why subsonic airfoils don't work at supersonic speeds is because they have the blunt nose that makes them actually fly well at subsonic speeds. So what that happens is it makes the sonic boom, the shock wave, detached, because the air will just sort of ram into the front of the wing and it'll get stuck. What the supersonic airfoil does is it has a point at the front, and that makes the shock waves attached to the wing, which greatly reduces the drag.
Could you re-explain that?
Okay. Sorry. The reason why supersonic airfoils have the pointy front is to reduce drag by making the shock wave attached to the wing instead of detached in front of the wing and causing a massive pressure increase in the front of the wing.
Okay, so for a subsonic thing, you fly really fast. Because it's blunt on the front, it pushes air forward. It doesn't allow it to.
So at supersonic speeds, the blunt front of the subsonic airfoil causes the sonic boom to not be attached to the aircraft itself.
Why is that?
Because the way I had it explained to me is the shock wave the shock wave is at a different angle depending on the angle between the wing and the airfoil. So, like for this wing, the shock wave would be about there. If this were steeper, like if the wing itself were like there, the shock wave would be nearly vertical. For this, essentially, what it looks like if you expand it way out is at the very front of the wing, there's just a vertical wall. And when supersonic air hits that vertical wall, it compresses a lot. And that causes the shock wave to appear further out. Yeah.
Is that why there's like a bit of drag spike once you get closer and closer to supersonic speed? Or whatever, the drag spike, I guess?
Yes. Yeah. That's part of the reason. The other part of the reason is because air gets concentrated in different areas of the aircraft. So if there's an area that air just sort of naturally flows faster towards, faster in, then that area will reach supersonic speeds before the rest of the aircraft.
Okay.
So you'll end up with a shock wave that is detached and weirdly shaped. And the shock waves that I was talking about, that like they form nicely on this wing and they're like this angle. Those only form above like Mach 1.4. So anywhere from like Mach 0.9, well, Mach is the speed of sound. So anywhere from 0.9 times the speed of sound to around 1.4 times the speed of sound, you have weird stuff happening. Most people tend to ignore that. They just until you get into the later like fluid modeling courses where you actually just have a computer do all the equations for you because they're too complicated to do by hand. So interesting thing. So you see the early airfoils were really thin. The later airfoils, they got thicker. So there's an interesting reason behind that, and that's wind tunnels. So the people designing the wings couldn't build a wind tunnel good enough to accurately test their wings, so they just opted for a bad wind tunnel, which gave them a bad design, which they then did not actually test before putting on a plane, which just... So up until like halfway through World War I, we just had bad planes, and there was no way to improve it. I think the first plane with an actually decent airfoil to fly was, what was the plane that the Red Baron?
Buckworth D3. Yeah.
And that one outflew every single plane in a dogfight. Not because it was more powerful or because it had better guns, but simply because it generated less drag and more lift. And that's all that was necessary to just create a dominating fighter. It was a pretty good jet, wasn't it?
The D3?
No, sure.
The triplane?
Triplane.
Yeah.
Pretty good plane.
Yeah.
Okay, so we have all so back to the pressure differential. So all that matters is the pressure differential. So if you can make that pressure differential, if you can make the flow term, who cares what your wing looks like? So someone had this idea, and so you know how when you throw a baseball, if you put spin on it, it curves? The same would happen for a cylinder. So this works. This flies. This is an RC plane strapped to some KFC buckets. So the basic idea, you can see on this side. These lines are streamlined, so essentially air is just moving along these lines. So you can see the air comes to a stop here around this rotating cylinder. So the air comes to a stop there, which means it's really high pressure. It's being stagnated, and it's high pressure there. And so this whole area has pretty high pressure, and this whole area has low pressure. That generates lift. Now, it's not used because it's not nearly as efficient as an actual wing, but it still works. So, I have a little video to show a little bit of.
It was magnetic.
All right. And where's the motor?
Motor's there.
Yeah.
It's quite small. One.
So then you just got a runner. There's no elevator. All you can do it.
I'm not going to show the whole video, I'm just going to show part of it. So, do you think this will fly?
Yes. Consider showing it to us.
I mean, that video is like.
Yeah.
I mean, yo.
How do you control pitch without an elevator?
Use a propeller.
That rudder is a lot of work.
It looks like something from the mind of like Leonardo da Vinci.
Yeah.
Yeah,
This is just something that, by all means, should just fall out of the sky.
Wait, so explain how pitch works again.
So the propeller is located below the center of mass.
Oh, so you just stronger,
So,
it'll go
yeah.
up, weaker. Okay.
Yeah.
That's,
So we could watch this go around for any amount of time we want to, but we won't. So,
Defies the laws of common sense.
yeah. So another thing that defies the laws of common sense is what's called ground effect. Now we have 4 people doing hovercrafts. This is the whole reason why your projects work. So,
Russia.
yes,
Great
Russia,
job.
what on the world is ground effect? This is an actual physical plane. You can see the cockpit right there. It reaches a maximum of about 20 feet above the ground, and it doesn't generate enough lift to get any higher than that. So this is another thing that just doesn't look like it should fly. But essentially, ground effect is what makes it fly, and 8-gen engines. So, what is ground effect? So, essentially you have, in like free air in a wing far away from the ground, air just sort of moves down and it doesn't push back on the wing nearly as much as when it gets stopped by the ground and sort of get loops back up. It essentially creates a high pressure cushion. Sorry, I'd like to stop if anybody has questions about the magnetism. So, a hovercraft works the same way. There's essentially a high pressure cushion formed under the craft that creates an upwards force. So it's again just the pressure differential that creates force. And let's see. This is how hovercrafts work. Pretty basic.
What's skirt volume?
This is a cross section. So imagine someone cut this hovercraft in half, like this. So this, like fabric bit here, that is what's called the skirt of the hovercraft, and that goes around
Okay.
here. So you force air downwards, but not enough air to cause your entire craft to lift up, because then you just have a helicopter. So this is easier to build. This is easier to make fly than a helicopter because you don't need as much power, and you can afford more weight, like and safety features and things like that. So air is forced in, and a little bit of air goes to the skirt, not that much, just enough to keep it inflated. But what does happen is air gets pushed into here, and because there's a very small distance, this is like hugely exaggerated, like this should be like half an inch, if that, even on like a full-size hover.
1/4 the size of the arrow. Like 1/4 the size of the arrow. No distance between the.
Yeah, this is exaggerated for effect. But essentially, the air can only escape so fast out of here. And that's because of, again, the Bernoulli effect. So the air has to move really fast. Well, sort of the Bernoulli effect, some other effects as well. It's complicated. It involves viscosity of the air and friction on the ground and the skirt. Essentially, the end result is the air can only move so fast through this corridor, which means if the skirt is too close to the ground, then the pressure on the inside will increase, causing a hovercraft to move up. And if the skirt is too high, the pressure will decrease, causing the skirt to move down.
So it balances itself out.
So it balances itself. That's it. So, does anybody? Yeah.
Oh, you know for those World War I airplanes?
Yes.
Why did they need a propeller?
So they needed a propeller because you need a way of pushing the aircraft forward. So a propeller is actually just two wings or some number of wings that are attached to a drive shaft. They create, well, we call it thrust, but it is really just lift in the direction of motion.
So they just spin really fast?
Yeah.
And what does that cause? Does it cause like?
So it causes the aircraft to be pushed forwards because it deflects air backwards.
Doesn't it also deflect air forward as well?
No. Why? No. Yeah, it doesn't deflect air forwards because the wings are angled so that it doesn't. Or that the propeller's angled so it doesn't. You could reverse the direction of the propeller and then you get thrust forward and not backwards.
Have you ever seen like the T-95, for example?
T-95.
Okay, in general, why would you ever have propellers and jet engines on a plane? Like the B-52 had in the beginning.
Okay.
Or is like one more efficient at certain altitudes and then they switch?
Propellers are much better at low altitude, low speed.
Okay.
Is the T-95 that massive
Russian bomber, yeah.
Yeah. Does that have jet engines, or is it just a turboprop?
That was a turboprop. T95.
Yeah.
Okay,
So
then what
that,
am I thinking of?
TU-165.
you might have been thinking of that. So, yeah. So the problem with, let's see. So that uses a jet engine. Well, it uses a turbine engine to turn the propeller.
Yeah, no, I was just making confusion with T-95. My question was just propellers and jets at the same time. So that's just altitude?
Yeah, so jet engines generally produce much less thrust at low altitudes compared to...
But isn't there more air to be pulled into the engine? And...
Well, they produce... They don't increase as fast. So
Okay.
you can build,
A plane has a
it's
jet engine.
easier to build a propeller craft that generates a good amount of thrust at low altitudes than
Okay.
a jet. Obviously, modern jet engines, you can get really high amounts of thrust, but like a turboprop would work pretty well too.
Actually,
Yeah.
one more question. Aircraft from World War II might have a climb rate of like 20 meters per second.
Yeah.
That's actually maybe like 17, 18.
Yeah.
But now you have planes with like, I don't know, can you give me a number? a lot higher.
Well, I mean, yeah, a lot.
Like,
I don't know.
Maybe like over 100 meters per second.
Yeah.
But then you had that like gray area, like for example during Korea, for example, where you had jet engines, but you still had a climb rate of like 30 to 50 meters per second. What caused that?
That's because jet engines weren't as good back then.
Okay.
So, honestly, I could talk for hours about jet. Well,
We don't have time for that.
yeah, the history of jet engines, it's long. In fact, early jet engines, a jet engine could be heavier than a piston-powered engine and produce less thrust.
Okay.
Yeah, they were pretty bad at the beginning.
M163 rockets. You go for it.
Yeah.
So could you explain like what a jet engine is?
Okay. Yeah. So a jet engine, it's a turbine engine that produces thrust with a hot jet of air that pushes back. Let me pull up a cross section.
How is that any different than a regular just propeller?
It's because you compress the air, right? Air compression. You have the compression. In the middle.
There's a difference. So. So these, that's a really bad picture. Okay. So these are all different propeller blades. And this is a turbojet, I think. So in a conventional piston engine, there are individual pistons which push a drive shaft. They fire intermittently and push a drive shaft, which then turns the propeller. In a jet engine, there's one drive shaft that runs the entire length of the jet, and with the exception of, I think, one company, there's no gearing whatsoever.
What company?
I don't know. I just know they have the patent on it, so there's only one. So essentially, all these blades are angled specifically to turn the low pressure, low velocity air into high pressure, high velocity air. And then it goes through the combustion chamber, which is a continuous combustion as opposed to a piston, which is like repetitive, just keeps firing. And so you have a continuous combustion, and that turns the high pressure or high velocity air into higher pressure, higher velocity air, which pushes this turbine, which causes these to spin. However, that's not what generates thrust on a turbojet. The exhaust coming out the back is what causes the thrust. So
How do you start the engine then? Like you need the air to start it?
there'll be like a drive shaft. There'll be like a gear that sticks out to a drive shaft and you turn the drive shaft. Or there'll be an electric motor inside. Sometimes there's like an air, sometimes there's like a, I know on commercial jets, if you get one engine started, you can use the other engines. You can use that engine to start the other engines. There's like an auxiliary power unit that can supply enough power to start the engines. And to start the first one, there's like an outside diesel generator that you just hook up to the jet. And this actually differs from modern commercial airliner designs, where in addition to all of this, the vast majority of the thrust is not caused by the exhaust. They essentially stick a massive fan that's like, relative to this, like the bottom would be like here. These things are big. I think GE is like 16, like the front, the main fan is like 16 times larger than this. So they get massive amounts of thrust out of that, and that just ups the efficiency at the expense of like instantaneous thrust. Any more questions? We're out of time. No one? Yes.
So large airplanes usually have like that sort of engine, right?
Yeah.
But you know in the B-2 bomber,
Yeah, how does that work? It like
Yeah.
intaked and then it closed the intake and then it blew up and then it opened the intake and then closed it. And then, how does that?
What?
The V2, because that's how it worked, right?
I have no idea.
Like it opened, like it had an intake and then it had a combustion in the same place. So it opened the intake to get air and then it closed it and then it combusted the air to throw it out and then it opened
Like
and closed the intake really fast.
I don't think,
It was a weird design.
I don't think that's correct.
Me neither.
There are planes that the intakes change their shape based off what altitude and what speed they're flying.
Yeah, like it like opened and closed quickly so that it could open and then get air in, and then when it closed, it would combust so that the air couldn't escape out the intake and it would only go back. It would just do that really quickly. I'm not I think that's how it
I'd have to double check that. I'm
Yeah.
not actually familiar with that. Yeah. Sorry, but that doesn't sound like any drive system I'm familiar with.
Do you mean with the V2 rocket?
Yeah.
Those were rockets with like fuel inside. There were 2-stage rockets.
no B-2 bomber.
Wait, V2 bomb?
No,
Oh, B2.
B2 bomb.
You said B2 bomb. I thought you said V2, like the German World War
The
II
V2
rocket.
Yeah, that's a rocket.
I can,
Wait.
oh yeah, so I can explain rockets, but that would have to wait for another time.
Wait, did you say B2 or
Yeah,
B2?
B2 bomb.
B2
Yeah.
bomb, okay.
We're out of time.
Okay.
Oh.
I thought you said V2 rocket.
No. Thank you.